NASA detected something that shouldn't be visible. A supernova exploding when the universe was less than 1 billion years old. The James Webb Space Telescope captured the death of a star from an era so early that galaxies were still forming, stars were still igniting for the first time, and the cosmic dark ages had barely ended. And this changes everything we thought we knew about how massive stars died in the early universe. Right now, we're looking at light that traveled for over 13 billion years to reach us. The supernova, designated JWST SN-Z7.3, detonated when the universe was only 6.7% of its current age. And it was first announced by something even more violent, a gamma-ray burst that tore through space at the speed of light. The supernova occurred at a redshift of Z-Mars 7.3, meaning the universe had expanded by a factor of 8.3 since the light left that exploding star. The gamma-ray burst that preceded it released more energy in 10 seconds than the sun will produce in its entire 10 billion year lifetime. James Webb's near-infrared camera had to operate at the absolute limits of its sensitivity to isolate the fading supernova light from its host galaxy, which appears as nothing more than a faint smudge. Dr. Andrew Levin, astrophysicist at Radboud University and lead author of the discovery paper, stated in December 2024, "This is the most distant supernova ever confirmed. We're watching a star die in an era when the universe looked completely different from today. Even more disturbing, this supernova shouldn't have been detectable at all. The expansion of the universe should have stretched and dimmed its light beyond recognition, but the violence of its explosion was so extreme that we caught it anyway." This discovery broke the previous distance record for observed supernovae by over 600 million years of cosmic time. Here's what should concern you most. If massive stars were already dying this way less than 1 billion years after the Big Bang, it means stellar evolution in the early universe happened far faster than our models predict. The first generation of stars lived and died in a cosmic eye blink. Think about it. Before we dive deeper into this cosmic revelation, if you want to stay updated on what could be the most important discovery about the early universe this year, don't forget to click the subscribe button and turn on notifications. Because what we're about to reveal will completely change how you understand the first billion years of cosmic history. And leave a comment telling us, what do you think we'll find when we look even further back in time? Let's talk about what cosmic dawn actually means, because understanding this context makes the supernova discovery even more profound. The term cosmic dawn refers to the period roughly 100 million to 1 billion years after the Big Bang, when the first stars began to ignite and the first galaxies began to form. Before cosmic dawn, the universe was dark. Not dark in the sense of nighttime on Earth, but truly, utterly dark. The universe was filled with neutral hydrogen gas, atoms with 1 proton and 1 electron, electrically neutral, and completely opaque to visible light. This period is called the Cosmic Dark Ages, and it lasted for roughly 100 million years after the Big Bang. During this time, the universe was cooling, expanding, and matter was slowly clumping together under gravity into the seeds of future galaxies. Then, somewhere between 100 and 200 million years after the Big Bang, something remarkable happened. The first stars ignited. These weren't stars like our sun. These were massive, short-lived behemoths, perhaps 100 to 300 times the sun's mass, burning through their nuclear fuel at extraordinary rates. They were formed from primordial gas that contained almost no heavy elements, just hydrogen and helium left over from the Big Bang. These first stars, called population 3 stars, have never been directly observed. They died billions of years ago, and their light has been redshifted into wavelengths that are extraordinarily difficult to detect. But their influence shaped everything that came after. When these massive stars exploded as supernovae, they seeded the universe with the first heavy elements: carbon, oxygen, silicon, iron. These elements then became incorporated into the next generation of stars and eventually into planets and life itself. The supernova detected by James Webb, JWST SN-Z7.3, is not a population 3 supernova. It's from a slightly later generation, a population 2 or early population white star, but it's still extraordinarily early in cosmic history. At a redshift of ZR 7.3, this supernova exploded approximately 770 million years after the Big Bang. The universe at that time was only 5.6% of its current 13.8 billion year age. To put that in perspective, if the entire history of the universe were compressed into a single year, this supernova would have occurred on January 20th. Now here's where the story gets remarkable. The discovery didn't begin with the James Webb Space Telescope. It began on March 14, 2025, when an observatory in space called SVOM, the Space-Based Multiband Astronomical Variable Objects Monitor, detected a flash of high-energy gamma rays coming from a specific region of sky. Gamma ray bursts, or GRBs, are among the most energetic events in the universe. They're flashes of gamma radiation, the highest energy form of light, that last anywhere from milliseconds to several minutes. They're so bright that they can outshine entire galaxies for brief periods. There are two types of GRBs. Short-duration GRBs, lasting less than 2 seconds, are thought to come from the merger of neutron stars or a neutron star colliding with a black hole. Long-duration GRBs, lasting more than 2 seconds, are associated with the collapse of massive stars, specifically supernovae of a particular type called collapsars. The GRB detected by SVOM on March 14, 2025, was a long-duration burst. It lasted approximately 23 seconds. That immediately suggested it was associated with a massive star's death. But the key question was, where did it come from? How far away was the source? Within hours, ground-based telescopes swung into action. The European Southern Observatory's Very Large Telescope in Chile was able to obtain a spectrum of the fading afterglow, the light emitted as the shock wave from the explosion plows through surrounding material. Spectroscopy is the key to measuring cosmic distances for extremely distant objects. When light travels through the expanding universe, its wavelength gets stretched. The farther the light travels, the more it's stretched. This stretching shifts the light toward the red end of the spectrum, hence the term redshift. By measuring specific spectral lines, emission or absorption features from hydrogen, oxygen, or other elements, and comparing their observed wavelengths to their known laboratory wavelengths, astronomers can calculate exactly how much the light has been stretched. That directly tells them the distance to the source. The Very Large Telescope's spectrum showed something extraordinary. The spectral lines were shifted by a factor of 8.3. That corresponds to a redshift of ZAB each, or 7.3. That placed the source at a distance of approximately 13 billion light-years. The light had been traveling for 13 billion years, meaning the event occurred when the universe was only 770 million years old. This was already remarkable. GRBs have been detected at high redshifts before, but ZR 7.3 places this in the top few most distant GRBs ever observed, but the real prize was still to come. GRBs fade quickly. Within hours to days, the afterglow dims below detectability for most telescopes. But if the GRB is associated with a supernova, there should be a secondary brightening over the following weeks as the supernova itself becomes visible. Supernovae and GRBs have different light curves, different patterns of brightening and fading over time. GRBs are fast, bright for seconds to minutes, then rapidly fading. Supernovae are slower. They rise to peak brightness over days to weeks, then fade over months. The challenge is that at extreme distances, both signals are incredibly faint. For a supernova at ZR 7.3, the light has been redshifted so much that visible light emitted by the supernova is stretched into the infrared by the time it reaches us. That's where the James Webb Space Telescope comes in. Webb is specifically designed to observe in infrared wavelengths, making it the perfect instrument for detecting highly redshifted objects from the early universe. Its sensitivity is orders of magnitude better than previous infrared telescopes. Approximately 110 days after the initial gamma-ray burst, the James Webb Space Telescope was pointed at the location of the GRB. The observation used Webb's near-infrared camera, or NIRCam, operating in multiple filters to build up a detailed image of the region. What the team saw was exactly what they hoped for: a faint point of light at the location of the GRB, separate from the host galaxy. That point of light was the supernova. But here's the challenge. At ZR 7.3, even bright galaxies appear as faint smudges. The host galaxy of this supernova is a small young galaxy that appears incredibly dim. The supernova itself, by the time Webb observed it 110 days after the GRB, had already faded significantly. Isolating the supernova light from the galaxy light required sophisticated image processing. The team had to model the galaxy's light distribution, subtract it, and then measure what was left over. What remained was the fading supernova. Dr. Levin's team published their findings in the journal Astronomy and Astrophysics in December 2024. The paper's title is straightforward. JWST reveals a supernova following a gamma-ray burst at Z 7.3. That tilde symbol means approximately equal to. The redshift is measured as Z or 7.3 with some small uncertainty, but the measurement is robust. This is definitively the most distant supernova ever observed. But here's where it gets really interesting. The supernova's properties tell us something fundamental about massive star evolution in the early universe. By measuring the brightness and the rate at which it faded, astronomers can estimate the mass of the progenitor star, the star that exploded. The data suggest this was a massive star, likely between 20 and 40 times the mass of the Sun. That's massive enough to end its life as a core-collapse supernova and potentially leave behind a black hole. The fact that it was associated with a long-duration GRB confirms it was a collapser, a specific type of supernova where the core of the star collapses directly into a black hole, launching jets of material at near-light speed along the star's rotation axis. When those jets punch through the star's outer layers, they produce the gamma-ray burst. But here's the problem. Stars of this mass should take roughly 3 to 5 million years to evolve from birth to death. That might sound like a long time, but cosmically speaking, it's an eye blink. For a star this massive to have already formed, lived its entire life, and exploded as a supernova by 770 million years after the Big Bang, means that star formation in the early universe was incredibly efficient. The first stars had to form quickly, they had to be massive, and they had to die young. This is consistent with theoretical models, but seeing it confirmed observationally is different. Models are only as good as their assumptions. Observations don't lie. And there's another implication that's even more profound. When massive stars explode as supernovae, they don't just die, they enrich their surroundings with heavy elements. The star's core has been cooking lighter elements into heavier ones through nuclear fusion throughout its life. When it explodes, those heavy elements, carbon, nitrogen, oxygen, magnesium, silicon, iron, are blasted into space. Those elements then become incorporated into the next generation of stars and planets. The universe began with almost nothing but hydrogen and helium. Everything heavier than helium, everything we're made of, every atom in your body except the hydrogen, was created inside stars and dispersed through supernovae. The supernova detected at Z, JWST 7.3 was part of that cosmic enrichment process. It was taking the primordial hydrogen and helium from the Big Bang and converting it into heavier elements, seeding the early universe with the building blocks of planets and life. But here's where it gets unsettling. The host galaxy of this supernova is tiny. Based on its brightness and spectral properties, it probably contains only a few million to tens of millions of stars. That's a dwarf galaxy by modern standards. Our Milky Way contains roughly 200 billion stars, yet this tiny galaxy was already forming massive stars capable of exploding as supernovae and producing gamma-ray bursts. That suggests the conditions for star formation in the early universe were radically different from today. Gas in early galaxies was denser, hotter, and more turbulent. It was easier for gas to collapse under gravity and ignite as stars, and without heavy elements to cool the gas efficiently, the stars that formed tended to be more massive than typical stars forming today. This is exactly what the James Webb Space Telescope was designed to investigate. How did the first galaxies form, and what were the first stars like? And JWST SN Z7.3 is providing some of the clearest answers yet. But there's another piece of this story that makes it even more remarkable. The gamma-ray burst that announced this supernova released an enormous amount of energy. Calculations based on the observed brightness and the distance suggest the total energy emitted in gamma rays alone was equivalent to converting roughly 1% of the sun's mass directly into pure energy. That's approximately 2 × 10⁻47 joules. To put that in perspective, that's more energy than the sun will produce through nuclear fusion over its entire 10 billion year lifetime, released in less than 30 seconds. How is that possible? The answer lies in the extreme physics of collapsing stellar cores and black hole formation. When the core of a massive star collapses, gravitational potential energy, the energy locked up in the mutual gravitational attraction of all the particles in the core, is suddenly released. Most of that energy goes into neutrinos, ghostly particles that barely interact with matter and stream out of the collapsing core at nearly the speed of light. But a small fraction of the energy, perhaps 0.1% to 1%, goes into launching jets of material at relativistic speeds. Those jets plow through the star's outer layers, heating them to billions of degrees and accelerating particles to near light speed. When the jets break free of the star, they produce the gamma-ray burst. The fact that we detected this GRB from a distance of 13 billion light-years means the jets must have been pointing almost directly at Earth. GRBs are highly beamed. Most of their energy is concentrated into narrow cones along the jet axis. If the jet had been pointing even a few degrees away from our line of sight, we wouldn't have seen it at all. This introduces a selection effect. The GRBs we detect at high redshifts are only the ones that happen to be pointing at us. For every GRB we detect, there are probably dozens or hundreds happening at similar distances that we don't see because they're pointing elsewhere. That means supernovae like JWST SNZ 7.3 are probably happening all the time in the early universe. We just don't see most of them. And it gets worse. The universe at JWST 7.3 was smaller, denser, and hotter than today. The cosmic microwave background radiation, the leftover heat from the Big Bang, was not at its current frigid temperature of 2.7 Kelvin above absolute zero. At JWST 7.3, the CMB temperature was approximately 22 Kelvin, about 8 times hotter. That's still cold by human standards, but it's significantly warmer than the current cosmic temperature. More importantly, the higher energy photons in the early universe's radiation field affected how matter behaved. Gas couldn't cool as efficiently because the ambient radiation kept heating it. Star formation was likely more violent and explosive than in the modern universe, and supernovae in the early universe may have had a disproportionate impact on their surroundings. Because galaxies were smaller and less massive, supernova explosions could potentially blow significant amounts of gas out of the galaxy entirely, suppressing future star formation. This is called supernova feedback, and it's a critical process in galaxy evolution. Too much supernova feedback and galaxies can't grow. Too little, and galaxies would form stars too quickly and run out of gas. The balance is delicate, and we're only beginning to understand how it played out in the early universe. Dr. Levin's discovery paper includes another fascinating detail. By comparing the brightness of the supernova to theoretical models, the team estimated that the supernova ejected roughly 2 to 4 solar masses of heavy elements into its surroundings. That might not sound like much, 2 to 4 times the sun's mass. But remember that this galaxy only contains millions of stars, not billions. Adding several solar masses of heavy elements represents a significant enrichment of the galaxy's chemical composition. Over time, as more and more massive stars lived and died, the fraction of heavy elements in the galaxy would increase. This process is called chemical evolution, and it's essential for the eventual formation of planets and life. Our sun formed about 4.6 billion years ago from gas that had already been enriched by multiple generations of supernovae. The heavy elements in Earth, the iron in your blood, the calcium in your bones, the oxygen you breathe, all came from ancient stars that exploded billions of years ago. JWST SN Z73 is part of that story. It's one of the early chapters in the universe's journey from pure hydrogen and helium to the chemically complex cosmos we inhabit today. But here's where it gets really strange. The detection of this supernova was only possible because of a fortunate alignment of multiple factors. First, the star had to explode as a collapsar, producing a GRB, which provided the initial alert. Second, the GRB jets had to be pointing nearly at Earth. Third, the SVOM satellite had to be operational and looking at the right part of the sky at the right time. Fourth, ground-based telescopes had to respond quickly to measure the redshift. And fifth, the James Webb Space Telescope had to have observing time available 110 days later to image the fading supernova. If any one of those factors had been different, we wouldn't have detected this supernova. The universe is full of events like this: distant supernova, gamma-ray bursts, colliding galaxies that go unobserved simply because we're not looking at the right place at the right time with the right instruments. The James Webb Space Telescope is changing that. Its sensitivity and infrared capabilities are allowing astronomers to peer deeper into cosmic history than ever before. Since its launch in December 2021 and the beginning of science operations in July 2022, Webb has discovered galaxies at redshifts approaching ZI-E 14, corresponding to the universe at only 300 million years old. It's found supermassive black holes that shouldn't exist yet in such a young universe. It's detected organic molecules in exoplanet atmospheres. It's revealed the structure of distant galaxies in unprecedented detail. And now, it's confirmed the most distant supernova ever observed. Dr. Levin's team is already planning follow-up observations. They want to search for more high redshift supernovae to build up a statistical sample. One object is interesting, but it's not enough to draw broad conclusions. Multiple detections at similar redshifts would allow astronomers to study the properties of early supernovae as a population. Are they all this massive? Do they all produce GRBs? How much heavy element enrichment did they provide on average? These are questions that can only be answered with more data. Now, let's put it all together. A massive star exploded as a supernova 13 billion years ago when the universe was only 770 million years old. The explosion produced a gamma-ray burst that traveled across the cosmos for 13 billion years before being detected by the SVOM satellite on March 14, 2025. Follow-up observations with the Very Large Telescope confirmed the extreme distance, and 110 days later, the James Webb Space Telescope captured the fading supernova light, the most distant supernova ever observed. The probability of detecting such an event, requiring a perfectly aligned GRB, rapid follow-up spectroscopy, and Webb observing time at exactly the right moment, is extraordinarily low. We got lucky. We're not saying supernovae at cosmic dawn are rare. They're probably common. But catching one with this level of detail, at this extreme distance, with all the pieces falling into place, is exceptional. We've reached a point where even conservative astronomers are acknowledging that the early universe was more active, more violent, and more rapidly evolving than we previously thought. The James Webb Space Telescope has been allocated additional observing time to search for more high redshift transients, supernova, GRBs, and other explosive events from the first billion years of cosmic history. And here's what this really means. We're watching the universe grow up. We're seeing the deaths of some of the first massive stars. We're witnessing the chemical enrichment that made planets and life possible. And we're confirming that cosmic dawn was a time of extraordinary violence and transformation. Understanding these early supernovae isn't just about breaking distance records. It's about understanding how the universe transitioned from the simple, element-poor state it was in after the Big Bang to the complex, chemically rich cosmos we observe today. So, what do we know for certain? First, the supernova JWST SNZ 7.3 occurred at redshift Z-star 7.3, approximately 770 million years after the Big Bang, making it the most distant supernova ever confirmed. Second, it was associated with a long-duration gamma-ray burst, indicating the progenitor was a massive star that collapsed into a black hole. Third, the detection required the combined efforts of space-based gamma-ray observatories, ground-based spectroscopy, and the James Webb Space Telescope operating at the limits of its sensitivity. What don't we know? How common were supernovae like this in the early universe? How much did they contribute to the chemical enrichment of the first galaxies? What was the mass distribution of stars in cosmic dawn? Were most stars massive and short-lived, or did lower mass stars dominate? And here's the urgency. The James Webb Space Telescope is revolutionizing our view of the early universe, but it won't operate forever. Its fuel supply is finite. Its instruments, though remarkably robust, will eventually degrade. Because if the next generation of time domain surveys and gamma-ray observatories detect more events like this, and if Webb can observe them before its mission ends, we'll have an unprecedented window into the first billion years of cosmic history. The truth is this: massive stars were already living and dying less than 1 billion years after the Big Bang. The universe wasted no time igniting its first stellar furnaces and enriching itself with heavy elements. And we've just watched one of those ancient stars explode across 13 billion years of space and time. And the only way to understand the full story of cosmic dawn is through continued observation of these distant explosions before they fade beyond the reach of even our most powerful telescopes. If this video left you in awe of how far back in time we can now see, don't forget to click the like button and subscribe to this channel. We're tracking high redshift transients and early universe discoveries in real time, and you won't want to miss what happens when the next distant supernova or GRB is detected by Webb and other observatories. Leave a comment with your theory. How far back in time do you think we'll eventually be able to see? Will we ever directly observe the first stars? And share this video with anyone who thinks we've already discovered everything there is to know about the universe. After watching this, they'll never think about the early universe as a simple, quiet place again. It was a cosmic shooting gallery of exploding stars,